Okay, so in this lecture, we'll talk about equipotential surface. So, what is equipotential surface? It is basically the surface where is the locus of all points which are at the same potential. This is known as equipotential surface. No work is required to move the charge from one point to another on the equipotential surface. Okay, so we can also say this as any surface with electrical potential same at every point is termed as equipotential surface. So we have equipotential points as a next subtopic. So if the points in an electrical field are all at the same electric potential, they are known as equipotential points. If these points are connected by a line or a curve, it is known as an equipotential line. If the such points lie on a surface, that surface is known as equipotential surface. Further, these points are distributed throughout a space or a volume. It is known as an equipotential volume. So what we have to now our next subtopic is work done in equipotential surface. So work done in a moving charge between 2 points in an equipotential surface is zero. Why? If a point charge is moved from a point VA to VB, for example, in an equipotential surface, then the work done in the moving charge would be given by W equals to Q naught into VA minus VB. We know VA minus VB is equals to 0 since all of them lie on the same point, so the total work done would be equals to 0. There are further some properties of equipotential surface. The electrical field, okay, so we'll continue with the some properties, the important properties. The electrical field is always perpendicular to an equipotential surface. This is the first property. Two equipotential surfaces can never intersect. This is the rule, and you have to remember this. And now we'll move on to the next property. For a point charge, the equipotential surfaces are concentric spherical shells. For an uniform electric field, the equipotential surfaces are planar normal to the x-axis. The direction of the equipotential surface is always from high potential to low potential. Inside a hollow charged spherical conductor, the potential is constant. This can be treated as equipotential volume. No work is required to move a charge from its center to the surface. For an isolated point charge, the equipotential surface is a sphere. That is, the concentric spheres around a point charge at different equipotential surfaces. In a uniform electric field, any plane normal to the field direction is an equipotential surface. Is a equipotential surface. And the last point is the spacing between the equipotential surfaces enables us to identify regions of strong and weak field. That is E equals to minus dV upon dr, and E is inversely proportional to dr. In this image, you can see that there is a tangential plane, which is also an equipotential surface. So that's it for today's video, and stay connected to Toppers Academy. Thank you.